Out there in the vast expanse of the cosmos lurk objects of immense power and mystery. We call them black holes. Imagine a place where gravity is so strong that nothing, not even light, can escape. These are black holes, cosmic monsters that have captivated our imaginations for decades. Their very existence challenges our understanding of the universe. They are a testament to the immense forces at play in the cosmos. The mystery surrounding black holes stems from their very nature. We cannot see them directly. Their gravitational pull is so strong that it warps the fabric of space-time. This warping prevents any light from escaping, rendering them invisible to our telescopes. Yet we know they are there. We can see their effects on the surrounding stars and gas. Like moths drawn to a flame, we are drawn to these enigmatic objects. We yearn to understand their secrets, to unravel the mysteries they hold. Black holes represent the ultimate frontier of our knowledge. They are a challenge and an inspiration, urging us to push the boundaries of human understanding. Imagine a giant star much larger than our Sun nearing the end of its life. This star has lived for millions of years, shining brightly in the cosmos, but now it is reaching a critical phase. It has burned through all its fuel. The hydrogen and helium that powered its nuclear fusion reactions are now depleted. The outward pressure from nuclear fusion, which once balanced the inward pull of gravity, can no longer hold back the relentless inward pull of gravity. The star's core begins to contract under its own immense weight. The star collapses in on itself, crunching down to an unimaginably small point, a process that happens in a matter of seconds, but involves forces and energies beyond human comprehension. This point, called a singularity, is where gravity becomes infinitely strong. The laws of physics as we know them cease to operate in this region. This singularity, shrouded by an invisible boundary known as the event horizon, is what we call a black hole. The event horizon marks the point of no return. Cross the event horizon and there's no turning back. Anything that crosses this boundary is inexorably drawn towards the singularity. The gravitational pull within this boundary is so strong that escape becomes impossible, even for light itself. This is why black holes appear black. No light can escape to reveal their presence. But how do black holes form? The process is both fascinating and violent. They are born from the death throes of massive stars. These stars, much larger than our Sun, live fast and die young in cosmic terms. When these stellar giants exhaust their nuclear fuel, they can no longer support themselves against their own gravity. The core collapses under its own weight. The core collapses, imploding in a spectacular supernova explosion. This explosion can outshine an entire galaxy for a brief period. What remains is a region of space-time so dense that it curves in on itself, forming a black hole. This curvature is so extreme that it traps everything that comes too close. Black holes are not cosmic vacuum cleaners, though. They don't roam the universe sucking in everything in their path. They have a gravitational pull, just like any other object in space, that depends on their mass and distance. Objects can orbit black holes just as they orbit stars. The gravitational influence of a black hole is determined by its mass and the distance from it. The closer you get, the stronger the pull. If our Sun were to suddenly become a black hole, Earth wouldn't be sucked in. The mass of the Sun would remain the same, so the gravitational pull on Earth would be unchanged. We would continue orbiting as usual, albeit in perpetual darkness. The Sun's light and heat would be gone, plunging our planet into a cold, dark existence. Black holes can also have accretion disks, which are formed by matter spiraling into the black hole. These disks can emit intense radiation as the matter heats up. Some black holes even produce jets of high-energy particles that shoot out at nearly the speed of light, a phenomenon that is still not fully understood. Black holes can also merge with other black holes, creating even larger black holes. These mergers release gravitational waves, ripples in space-time that we can detect with instruments on Earth. Many galaxies, including our own Milky Way, have supermassive black holes at their centers. These black holes can have masses millions or even billions of times that of our Sun. The study of black holes is one of the most exciting fields in astrophysics. With each discovery, we learn more about the fundamental nature of the universe. As technology advances, we will continue to uncover the mysteries of these enigmatic objects, pushing the boundaries of our understanding of the cosmos. As you approach a black hole, the fabric of space-time itself begins to warp dramatically. This warping is not just a simple bending or curving, it is a profound distortion that affects everything around it, including light, time, and matter. Picture a trampoline with a bowling ball in the center. The trampoline surface represents the fabric of space-time, and the bowling ball represents the black hole. The ball represents the black hole, and the trampoline surface represents space-time. As the ball sits in the center, it creates a dip in the trampoline, pulling everything towards it. Just as the bowling ball creates a dip in the trampoline, a black hole creates a well in space-time. This well is incredibly deep and steep, pulling in everything that comes too close. This well grows steeper and deeper as you get closer to the black hole. The gravitational pull becomes stronger, and the effects on space-time become more pronounced. As you get closer to the event horizon, time itself slows down for you relative to someone observing from a safe distance. This means that while you might feel like only a few moments have passed, an observer far away would see time stretching out endlessly. This phenomenon, known as time dilation, is one of the most mind-bending predictions of Einstein's theory of general relativity. It challenges our everyday understanding of time and space, showing us that they are interconnected and can be warped by gravity. To an outside observer, you would appear to slow down as you approach the event horizon, your image redshifting until it fades from view. This redshifting occurs because the light waves emitted from you are stretched to longer wavelengths, making you appear redder and dimmer. The event horizon is not a physical boundary like the surface of a planet. It is an invisible threshold where the escape velocity equals the speed of light. Instead, it is a point of no return. Once you cross this boundary, the gravitational pull is so strong that nothing, not even light, can escape. Once you cross it, there's no coming back. You are inevitably drawn towards the singularity, the core of the black hole, where gravity is infinitely strong. The gravitational pull inside the event horizon is so strong that not even light can escape its clutches. This is why black holes appear black. They trap all light within them. What would you see as you fell into a black hole? The experience would be unlike anything else in the universe. The answer, surprisingly, is not nothing. You would see the universe around you becoming increasingly distorted as you fell deeper into the black hole's gravitational well. As you plummet towards the singularity, the intense gravity would distort the fabric of space-time around you. This distortion would stretch and squeeze everything, creating a surreal and disorienting experience. You would witness the universe around you warp and distort in bizarre and unpredictable ways. Stars and galaxies would appear to twist and stretch, and the very fabric of reality would seem to bend and contort. This journey into a black hole would be a one-way trip into the unknown, a voyage into the most extreme and mysterious regions of the cosmos. Imagine a spaceship venturing too close to a black hole. This isn't just any ordinary journey through space, it's a perilous adventure into one of the most mysterious and dangerous phenomena in the universe. As it gets closer, the gravitational pull on the ship's front end becomes significantly stronger than the pull on its rear end. This isn't a gradual change, it's a dramatic and sudden increase in force that can have catastrophic consequences. This difference in gravitational force across the length of the spaceship creates a tidal force, stretching it like a piece of spaghetti. Imagine the ship being pulled apart, its structure elongating and distorting in ways that defy our everyday experiences. This rather unpleasant phenomenon is aptly named spaghettification. The term might sound whimsical, but the reality is anything but. It's a violent and destructive process that leaves no part of the object unchanged. Spaghettification is not limited to spaceships. Any object, regardless of its compositional structure, would undergo this extreme stretching if it ventured too close to a black hole. Any object, even a human body, would experience this extreme stretching as it fell into a black hole. The human body, with its complex and delicate structure, would be particularly vulnerable to these forces. The tidal forces would elongate your body, stretching it into a long, thin strand, much like a noodle being pulled apart. This isn't just a theoretical concept, it's a real and terrifying possibility for anything that gets too close to a black hole. The closer you get to the singularity, the stronger these tidal forces become. The singularity is the very heart of the black hole, where gravity is so intense that not even light can escape. Eventually, the stretching would become so extreme that it would rip apart the very fabric of your being, atom by atom. This isn't just a physical disintegration, it's a complete breakdown of matter at the most fundamental level. It's a rather gruesome end but it highlights the incredible power of these cosmic behemoths. Black holes are among the most powerful and enigmatic objects in the universe, capable of exerting forces that are beyond our comprehension. But what if the black hole was smaller? Would the effects of spaghettification be any less severe? Interestingly, the spaghettification process would be less dramatic for smaller black holes. This might seem counterintuitive, but it's all about the distribution of gravitational forces. This is because the difference in gravitational pull between your head and your feet would be less extreme. In a smaller black hole, the gradient of gravitational force is not as steep, leading to a less intense stretching effect. You might survive a bit longer, but your ultimate fate would be the same. The black hole's gravity would still be inescapable, and eventually you would succumb to its overwhelming pull. The journey might be slightly less violent, but the end result is inevitable. Black holes are relentless in their consumption of matter. Anything that crosses their event horizon is doomed to be pulled in and stretched beyond recognition. This process is a stark reminder of the immense and unforgiving nature of the universe. The study of black holes and spaghettification continues to fascinate and challenge scientists. Theoretical physicists are constantly exploring these phenomena to better understand the fundamental laws of nature. Advanced simulations and observations are helping us to unravel the mysteries of black holes. Each new discovery brings us closer to understanding these enigmatic objects and the extreme conditions they create. The universe is full of wonders and dangers, and black holes are among the most awe-inspiring. They remind us of the limits of our knowledge and the vastness of the cosmos. As we continue our journey through space, the study of black holes and spaghettification will remain a crucial part of our quest to understand the universe. These cosmic giants challenge our perceptions and push the boundaries of science. The exploration of black holes is an endless journey, one that will continue to captivate and inspire future generations of scientists and explorers. The unrelenting grip of spaghettification is just one of the many mysteries that await us in the vast expanse of space.